We have a lot of physicists today on our stage again. That goes also for our next speaker. His name is Marc Geitz. He's an innovation architect in the Telekom Innovation Labs. And he works for 20 years, for more than 20 years already in the telecommunication industry, has a lot of experience there. And in the T-Labs, he's since 2013. Hello and welcome, Marc. It's great to have you here. And you are also going to talk about quantum key distribution and other things, I think, especially with focus on the Open QKD testbed here in Berlin. So let's hear your talk. Thank you very much for being with us, and the stage is yours.
Okay, thank you very much. Can we just do a sound check? Does it work? You hear me?
It works perfectly, and we can also see your slides.
Perfect. Okay, so the talk, first of all, good morning to everybody. So the name of the talk is State of the Art of Making Communication Quantum Secure. In principle, we could also have named it, let's say, our experience with the Open QKD testbed that's been ramped up in Berlin. And I'm giving this talk, but I'm giving this talk for a quite large group of people, yeah, as you see. So there are a couple of people on the left side that really were active building the testbed. And Open QKD is a larger scope where we have architects and certification and security colleagues. They're also joining the project. Myself, I'm working for T-Labs, Telekom Innovation Laboratories in Berlin, with the scope of investigating technology that is 3 to 5 years ahead of now, and what's the impact of this technology for a telco business. One of our blue chips is secure future networks, and this is why we investigate quantum secure communication. To intro, so I go through these first slides rather quickly because I think you've seen many of these points already, but I don't know. So quantum computers, I mean, you can see as good or as bad guy. Yeah. So I mean, you probably listened to some talks already where people actually project the possibilities that you can do with quantum computers in the future. I mean, you could do so many amazing things that you can never do with any traditional systems. But if you have such a powerful thing, I mean, there's also the turn side of things. Quantum computers can also attack nowadays communication system. And this really goes to the heart of the telco industry, yeah, because we're selling secure communication. And that's why we're interested. Is the threat real? You can answer this with a clear yes. Yeah. So what I brought here is the IBM roadmap that has been published. It has been published, I think, only to 2028, but I took the factors of doubling the qubits, right? And in 2031, they claim, according to this, that they will have a quantum machine of 20 million qubits extrapolated. And there was another paper in 2019, yeah, where the authors claim that they can break RSA with 248 bits in 8 hours, yeah, using 20 million noisy qubits, which is exactly what IBM is projecting. So we have 10 years. Yeah, and 10 years is not a lot of time, yeah, to, let's say, renovate your security environment. But we need to start, and we already started. Just to summarize the two kinds of cryptography that we are investigating. So we have symmetric cryptography and asymmetric cryptography. In the symmetric case, both parties, Alice and Bob, share the same key. You have the data encrypted and decrypted with the same key. And the communication works as such. On the other hand, there is asymmetric crypto, yeah, where you have, let's say, a private key and a public key, and the encryption works in a way that you use your traffic with a public key encrypted, then the other party uses the private key or his or her private key to decrypt the data, and the communication works. Yeah. The unfortunate thing is that everything that is nowadays and asymmetric doesn't work anymore. Yeah, it's been broken by, it will be broken by Shor's algorithm or by similar approaches by quantum annealers. If that's actually the roadmap of the vendors continue as mentioned. Also, the symmetric one, I mean, is not completely safe. Yeah, so BSI and NIST, they claim, let's say, if you continue to use AES 256, you can encrypt about 1 terabit of data, yeah, or 64 gigabytes of data, which is not a lot. Yeah, so in our core networks, for instance, I mean, we ship multiples of this, yeah, in minutes or even in seconds. So we need, let's say, a constant and continuous flow of keys. So what can we do about this? So currently there are, let's say, two state-of-the-art technologies in place. One is post-quantum cryptography, PQC, and the other one is quantum key distribution. Both have pros and cons. So PQC on one hand is, let's say, more or less exactly the same that we have, but the underlying mathematics is a lot harder. So if you look on the pro side, it's still a software solution, that you actually can implement agile if you can. It works synchronous and asynchronous, and as I said, it can be made agile. On the downside of things is, and this is actually the biggest downside, there is no security proof existing that PQC will sustain safe, let's say, forever. So the PQC algorithms, they need to be more monitored, and you have to be aware what's happening out there if your security system remains safe, and it's a little bit slower. On the other hand, there's quantum key distribution, which is a completely different approach. Here you say you exchange keys with a separate hardware platform, and you use quantum physics actually to secure that. And you can even get tracked on, or you can even see when your system is attacked, by monitoring certain KPIs. The downside of things is, unfortunately, it's a hardware solution, so it's very, very expensive, at least today. And it's synchronous only. Unfortunately, there is a 100-kilometer reach limit, for these QKD systems, because the single photons or the quantum states in general, they are actually damped away in the glass fibers or through the air. And one big problem is there are technical side channels available. So I mean, these systems can be hacked like any technical realization of a physical concept. And you have to, let's say, do a tremendous effort to secure systems. Just to summarize, I mean, the two encryption patterns that we also look at the time being in our testbed. One is key exchange through QKD or PQC. I mean, you can do both, and afterwards use a symmetric encryption pattern to encrypt your data. And on the other side, there is still asymmetric crypto working with PQC, with public and private keys. And this might be the solution if we want to continue with our e-commerce, or banking, or whatever we do today in the internet. So we can keep our finger crossed, that these algorithms work out. So the main pitch that I want to give in my talk is actually, there is not just PQC or just QKD. I mean, there are technologies that can make our network safe. And we should use actually every technology in the best possible combination as defense line, to, let's say, continue to have secure future communication. And this is, let's say, our guideline, what we did in our OpenQKD testbed. So it's not so well known. So Deutsche Telekom is one of the consortial partners of OpenQKD. OpenQKD is a European-wide project with lots of partners. And the aim here is to bring QKD technologies into the field, and to implement lots of use cases, to show the technology is working. What's not so wide known is there is a working and operating testbed, one of the 4 large ones even, in Berlin, operated by us, by Deutsche Telekom, together with actually all the other partners, or lots of them, that are here on the board. Let me show you the testbed. So we're located in Winterfeldstraße in the center of Berlin, and there's a lab environment. So this is where the servers are actually located at the time being. And we have field fiber in Berlin. So this is free configurable dark fiber or lit fiber. We can do whatever we want. And we're actually currently using loops of different lengths. So from Winterfeldstraße, WFD, we can loop to Ernst-Reuter-Platz, to some network operating centers, or even 100 kilometers out to Strausberg and back. This is the fiber we are using. And the lab as such, I mean, it's called the Open Lab Berlin. We're actually having 3 cabinets in there at the time being. And you see here the pictures of the cabinets. So going from top to down, I mean, you see servers. These are the servers running our, let's say, our key management, our virtual environments, our user applications. Underneath, you see a HSM, which is a hardware security module. It's an extra hardware device that's only been made for storing encryption keys in a very safe way. In the ultimate way, they would actually destroy themselves, yeah, if they're getting hacked. Not this one, that's an easy one, I would say. Underneath, there are two QKD systems from IDQ. We have one operating in the C band, the other one operating in the O band. Further down, two QKD systems from Toshiba, operating in the same bands. And on the very bottom, there's ATFA environment, which is the optical endpoint, connecting all the fibers I showed you. And there are also BSI encryption cards included to do the encryption on the optical layer. And vice versa on the other on the other two cabinets as endpoints. And the back of the racks you see here, I mean, you see the backside of the server, you see switches, you see routers. Yeah, so this is actually, I mean, for the IP segment of that, I mean, that's the endpoint and the connect to the internet, if you like. Beneath there are two level 3 encryptors from Thales. Yeah, they're Mistral devices. They are encrypting VPNs on level 3. More switches. There's an IDQ QRNG, yeah, that we also use for generating random numbers, yeah, that we forward across the stack. And underneath there is some test equipment and also a 5G gateway. Yeah, so we have a 5G integration here in that test bed because we also want to work on shipping encryption keys over the wireless cellular internet. So just check the time, 10 minutes, so I'm good in time. So this is the architecture that we ramped up or set up in our test bed. On the very bottom, I mean, it's a layered architecture. Yeah, we have a quantum layer, a key management layer, and application layer. So at the beginning, I want to focus on the quantum layer. So on the right side, you see QKD systems, the ones I just showed you. I mean, they're connecting every node, but here on the system, it's only between node 2 and 3 shown. I mean, they do their usual task. They're exchanging keys. Yeah, they're producing distributed keys. They can be used later on for encryption. We do this on different bands with different vendors, yeah, and we try to set up an architecture that is QKD vendor agnostic. Yeah, so in principle, it should be possible to put any QKD vendor into the stack, and it should work right away. This is what we just do with IDQ QKD systems. Yeah, I mean, on the top, you see the key production rate over time. You see they make about 1,800 key bits per second. And underneath, I mean, these are the KPIs I mentioned before. So the quantum bit error rate, yeah, which is about 3% if everything runs okay, or the QKD visibility. I mean, they're checking the coherence of their laser, of their very, very weak laser pulse, if you like. So it's also about 97%. And if something goes wrong, yeah, these KPIs would go up. Yeah, qubit error rate goes up, visibility drops down. And then you can actually see how you're attacked and you have to do something, right? The other part is a PQC actor that we implemented. Yeah, so PQC, post-quantum crypto, we use also to exchange keys. Yeah, it's another method. Yeah, so we actually do this over the internet, over the 5G wireless internet. Yeah, to mobile clients. Yeah. And that's kind of interesting, yeah, because I mean it's a different way of security. It's by complexity and not by physics, but it takes away all the limits, yeah, limitations of length, of spread, yeah, of it's network agnostic. I mean, you remember the pros and cons. And one of my what I do every day, at least. I mean, our lab is located in Berlin. Yeah, I'm sitting in Hagen, yeah, this city in North Rhine-Westphalia. And when I connect to my lab, yeah, so I mean, I can exchange keys. So I just let the movie run. But what I exactly do is I have more than one line, if you like, yeah. And I use, let's say, on one time I use, let's say, one PQC algorithm and one authentication scheme. The next message gets the next one. So Saber, Dilithium, Entru, Rainbow, Kaiba, Falcon. And then in principle, whatever I get, yeah, they're all different random numbers, if you like, I XOR them, yeah, and then I created such a robust combiner setup that I would say is, let's say, a pretty good step to exchange keys using PQC algorithms over long distances, and can also be used, let's say, to put a second factor on a quantum on the quantum line, yeah. So that does key exchange by QKD, yeah. So in principle, that is our thinking. Yeah, so we combine PQC, QKD to make it safer and somehow deploy this here in this testbed. Well, how does it go on? Here we go. I missed one. So this one, then it goes on to the next level, so the key management level. Yeah, so everything that produces keys, be it PQC and a PQC actor or various QKD devices, they ship their keys into a HSM. Yeah, so this is in this architecture the single point of truth. Yeah, so everything that is in the HSM can be used for encryption later on. Yeah, and this makes this architecture, let's say, QKD vendor agnostic. On the top of that, we have a user key management. Yeah, that is shipping keys to the users, to user applications or the encryptors. So in principle, this is offering ETSI interfaces, standard interfaces, giving keys and key IDs, or giving a key by a key ID. Yeah, and by that, the two, let's say, two different users, be it encryptors like the ADFA boxes I showed you, or the Thales VPN devices, or any applications that we write ourselves. Yeah, they can get, let's say, the same keys on both sides of the infrastructure, and can, let's say, use that to create a AES tunnel or something like this. There's another key management in here. It's a provider key management. This is the implementation of a key forwarding via a trusted node. You know? So if node 1 and node 3 want to communicate with each other, and they don't share QKD keys, for instance, they have to create a random number here, yeah, encrypt it, send it to node 2. Node 2 decrypts, encrypts again with node 3, send it to node 3, and then node 1 and node 3 have the same encryption keys they can use for encrypting their payload. The big downside of that is, yeah, in principle, the random number is clear in the intermediate node. Yeah? But what we did here is we put another post-quantum encryption layer on top of it. Yeah, so that is, let's say, encrypting the random number between 1 and 3, and then we ship it across this line. And this, I would say, it's a safer way of sharing that random number than just doing QKD alone or just doing PQC alone, which is again in accordance to our thinking, guideline of thinking here. Yeah, this already brings me to my last slide, just a summary of what we did. So we think that we implemented a target QKD architecture vision for our company. And we did this together with our colleagues in the other functions of DT. And we are actually implemented an architecture consisting of a key creation, yeah, by PQC or QKD or whatever, a key storage, a key management, and a key usage. And the only thing that is missing here is actually a control layer, yeah, that's sitting on top and steering it all. We have a key management layer that is supporting PQC communication. Yeah, it's really safe, yeah, in multiple ways. It works symmetric, yeah, using the key encapsulation mechanism. So it's just like key exchange, and it works asymmetric, securing, let's say, the lines where we have both endpoints under our control. We have a hardware security module, yeah, as a single point of truth in between. We can do key forwarding, and we can run a couple of use cases like securing SRTP sessions, WebRTC sessions. We can set up SOCKS 5 proxy lines, yeah, between, let's say, mobile clients and servers. And this is in principle all working in our testbed. So next steps that we are planning is co-propagation. Since everything now, the management and is set up, the integration into the telco world, I would say the next step is then really to look on the fiber and see what we can do to improve our KPIs on the optical layer. Yeah, so I mean, if you run on a dark fiber, I mean, you most probably get the highest key rates, but it's expensive for a telco operator. Yeah, in principle, what is more beneficial would be a co-propagation, yeah, or a lit fiber, where you have a quantum channel and a classical channel, let's say, on the same system. We want to see how this works with the nowadays available QKD systems and do our learnings from that. And we want to investigate further technology solutions here to enable quantum safety and quantum communications. Yeah, quantum communications, in my thinking, is not just key exchange. Yeah, there is a lot more. Yeah, but we have to, let's say, get ready for this. Yeah, and try to investigate and come up with solutions beyond security. Okay, that's all from my side. Thank you very much. Stay quantum safe, and now open for questions.
Marc, thank you so much for sharing with us your experiences in the OpenQKD testbed. There were a number of comments in the discussion. One you have already addressed yourself in the talk by pointing out that the system that you have showed us is actually vendor agnostic. There was another comment, I think, saying that post-quantum cryptography doesn't have to be slower. There are also very efficient solutions. For example, the solutions without PKI, as Rashid told us in the previous presentation. Maybe you want to comment on that or add on that?
Yeah, I mean, our framework is OpenQKD, or what we set up, yeah, but we're not focusing on OpenQKD only, yeah, on QKD only. Yeah, that should have become clear, yeah. So, I mean, what will make, or what technology, or what combination of technologies will make the race? This will be decided in the next years, yeah. So I think it must be simple, it must be cheap, it must do the job, yeah. And there is not one answer. Yeah? It also depends on the use cases. Yeah? I mean, for a telco operator, you need to secure your networks. Yeah, so QKD is very natural here. Yeah, so if you want to, let's say, secure your nodes, I mean, you have to communicate to your nodes. So QKD is a valid option. Huh? For end users, for instance, if they want to secure their internet access, yeah, I think nobody will actually deploy a QKD end station at their home. Yeah, maybe, but not in the next years, I would say. Yeah, so maybe QKD is the more native approach. Yeah, so and the combinations of such. Yeah, this is the goal of our investigation. Yeah.
Thank you once again, also for answering the questions and commenting on it. You will be further available for further questions and discussions in the Meet the Speaker section. So once again, to our audience, if you're interested, feel free to join Marc there for the next 15 minutes under the given link.